Hey, chemistry. I want to talk to you about this little term called Z effective. We've already talked about what Z is. Z is the same thing. It's still our nuclear charge, and our nuclear charge is dependent on the number of protons. Right? And so what we're looking at here is the same idea. We're looking at what the nuclear charge is, but we're actually looking at what the effective nuclear charge is. So when we look at this relationship between the protons in the nucleus and the outermost electrons, what we really want to look at is how much of a pull or how much of an attraction does that nucleus have on the outermost electron. And this looks different for different elements. If we look at hydrogen, for example, hydrogen, we have a 1 plus charge in the nucleus, and then we just have this one outermost electron on the outside, right? Well, that's different than lithium. When we look at lithium, we have a 3 plus charge on the nucleus, which is more than hydrogen, but we also have this, our outermost electron that's outside of the innermost electrons, right? We have inner electrons. Those inner electrons we call core electrons. We have these core electrons that are in between our nucleus, the protons in our nucleus, and our outermost electrons. Remember that our outermost electrons are called valence electrons, okay? So lithium already looks different than hydrogen, and this is kind of what we've been dealing with when we were talking about Coulomb's law. How does the attractive force between the nucleus and outermost electrons, how does that change as all of these factors change? How does it change when the protons increase? How does it change when the valence electrons in the valence shell change? How does it change when we get core electrons? And so what we've talked about with Coulomb's law is this force of attraction. When we're looking left to right, the dominating force here, or the driving force, the thing that drives the force of attraction moving from the left to the right on the periodic table, is nuclear force. Yes, we have additional electrons in the valence shell, but they don't make as much difference as the increasing protons in the nucleus make. And then we've looked at this top to bottom too. Top to bottom, in our periodic table, we do have increasing nuclear charge. We just saw it with hydrogen and lithium. Hydrogen has 1 proton, lithium has 3 protons, but we also have the outermost electron that's moving farther and farther and farther away from the nucleus. So which one's the more important force? Well, we determined that distance was more important in this case than protons. So why? That is the question that we want to look at today. Why is increasing distance more of an effect? Why does it have more of an effect than increasing protons when we're looking top to bottom in a family? And the key here are those core electrons. So let's look back. Let's revisit this idea of hydrogen and lithium. So I'm going to draw hydrogen again with its 1 plus nuclear charge. And it only has 1 electron. So 1 plus and a 1. And then lithium has a 3 plus charge, but it has 2 valence shells. The first shell is filled, or it has 2 electron shells. The first shell is filled, its core shell is filled with 2, and then it has 1 on the outside here. So does lithium feel that effect of 3 protons or not? And this is where Z effective comes in. So Z effective can be calculated. In order to calculate Z effective, or the effective nuclear charge, or the nuclear charge that that outermost electron actually feels, what we do is we take Z and we minus the core electrons. So in this case, what's happening is those core electrons act as like little soldiers with shields, right? So we have a nuclear charge in the middle. We have a nuclear charge of 1 in terms of protons for hydrogen. In lithium's case, we have 3, right? So greater number of protons in the nucleus, greater attraction, until you see that we have these little shields. So those core electrons act as little shields. It's almost like those core electrons, each core electron can shield 1 proton. And so this proton that's on the outside, it's not going to feel a nuclear charge of 3. It's going to feel a nuclear charge effectively of 1. Again, if we return up here to our little equation, we take our nuclear charge for lithium, which is 3, we subtract off the number of core electrons, which is 2, and we get an effective nuclear charge of 1. So that outermost electron for lithium is going to effectively feel an attraction as if there were only 1 proton in the nucleus. That is what Z effective is. So we see here that the attraction between hydrogen and its 1 proton of hydrogen and its 1 electron is going to be a pretty strong attraction. There's only 1 proton, but there's nothing in between, and those two can get really close together. This is going to be a pretty strong attraction for hydrogen compared to the attraction between that 1 outermost electron and that 1 proton that it effectively feels. Notice it's still only effectively feeling a pull of 1 proton, and it's farther away. So why is the radius of lithium bigger than hydrogen's? Because of this. It's really only feeling the same nuclear charge. Lithium's electron is feeling the same nuclear charge as hydrogen's electron, but it's farther away. Why is ionization energy less for lithium? Well, its 1 electron feels the same nuclear charge as hydrogen's electron does, but it's farther away. Why does it have lower electronegativity? Well, because the nuclear charge is effectively only 1. It's the same as hydrogen, but anything that it's trying to attract can't get as close. And so we see here this dynamic where distance really is the deciding factor, because nuclear charge is shielded from attracting anything or from its outermost electrons. So it's kind of an interesting concept that explains a lot. It kind of rounds out our understanding of Coulomb's law and why distance has more of an effect when we're looking top to bottom than those additional protons do. Now, Z effective also has an effect when you're looking left to right. So we can do a couple of these too. Let's look at lithium. And then we'll look at beryllium. Okay, so the difference between lithium and beryllium we see is nuclear charge. Again, lithium has nuclear charge of 3, beryllium has nuclear charge of 4. We also see that their core electrons are exactly the same, and then they have a difference in valence electrons. Lithium has 1 valence electron, beryllium has 2 valence electrons. So if we look at this, again, in terms of our effective nuclear charge, so what charge does the valence electrons feel from the nucleus? Okay, and then our core electrons are going to kind of shield or block the nuclear charge from the valence electrons. Okay, so our core electrons are blocking a nuclear charge. And then our valence electron is going to feel an effective nuclear charge from lithium of 1. And we can see that in the math too. So if we calculate Z effective, it's going to be 3 nuclear charge minus core electrons equals the charge from the nucleus that the valence electron actually feels. Same thing with beryllium. We'll calculate Z effective. It's going to be nuclear charge minus core electrons equals the charge that the valence electrons actually feel coming from the nucleus. So notice something. Notice that the valence electrons for beryllium are each going to feel a nuclear charge of 2. We saw in the Coulomb attraction models that each of those valence electrons feels the same nuclear charge. They don't really block nuclear charge from each other. So each of beryllium's valence electrons will feel a nuclear charge of 2 effectively. So notice that because they have the same amount of core electrons, lithium and beryllium are going to have different Z effectives. So why is beryllium smaller? Well, even though its valence electrons are blocked by those core electrons, it still feels an increased nuclear charge when compared to lithium. Why does it take more energy to rip one of those electrons away? Why does it have greater ionization energy? Well, it's at similar distance to lithium, and it feels a nuclear charge of 1 more than lithium feels. Why does beryllium have a higher electronegativity value? Why does it have a bigger ability to attract things to itself? Well, because the things that are outside of beryllium can feel a nuclear charge of 2. Whereas for lithium, they only feel a nuclear charge of 1. So the Z effective can help round out our understanding of periodic trends, both top to bottom in a group or a family, and left to right in a period. Okay, so let's pause here and just check our understanding. Why don't you calculate Z effective for magnesium and for fluorine. Okay. If this concept is confusing to you, you don't really need to be able to functionally deal with Z effective as long as you have embraced Coulomb's law. Left to right, protons make the biggest difference. Top to bottom, distance makes the biggest difference when we're describing forces of attraction. However, if you want to understand the bigger picture, then Z effective can provide that more complete, bigger picture to you. Okay, let me know what questions you have. I will see you in class.